All right. Here we go. Happy Monday. Of course, my dog is deciding now that it's time to bark at the mailman. So it goes. Yeah, we are here on a Monday, which is day 7 of Advent of Code. We are planning to talk about solving day 7 of Advent Code live online. The way this works is that I open up the problem, look at it, solve it, try to solve it in Go, or typically Go or Python, and we see what happens. So here we go. Just as a quick note, my name is Kent Quirk. I've been doing software engineering for about 40 years, about half of it in the game industry, and I'm just doing this for fun because these problems are fun to solve. They're good, interesting little bits of computer science, and people may find it interesting to watch somebody tackle these things. So that's what I'm doing, and I'm ready to roll. So here we go. We are going to open this and take a look at the problem. The fiction that we're following here is that we're slowly working our way through a trip. And so we've been making our way through the airport and onto the plane and onto the second airport. And now we're looking at what seems to be another airport puzzle. You land at the regional airport in time for your next flight. Flights are delayed due to issues in luggage processing. Many rules are being enforced about bags and their contents. Bags must be color-coded and must contain specific quantities of other color-coded bags. For example, consider the following rules, and then there's a set of rules. Okay. Light red bags contain 1 bright white bag and 2 muted yellow bags. Dark orange bags contain 3 bright white bags and 4 muted yellow bags. Bright white bags contain 1 shiny gold bag. Muted yellow bags contain 2 shiny gold bags and 9 faded blue bags. So there's what we have is container problem of some kind. So let's figure out what they mean about that. We're describing these bags with adjective, color, and a number. Toward the end of this list is faded blue bags contain no other bags. Dotted black bags contain no other bags. So it's basically describing a graph or a tree, and the leaves of the tree are sometimes point to other nodes in the tree or other nodes in the graph, and some of them contain no other nodes. So that's a fairly common description of a directed graph. And if you're looking things up computer science wise, you want to think about directed graphs. Now the question is whether this is a directed acyclic graph, meaning that the graph doesn't have any self-referential containment. I'm hoping that since they're bags, it doesn't, because once you end up with the possibility of recursion in a graph, it can get really ugly. Not recursion, looping. But let's assume this graph is acyclic until proven otherwise. The proof may well be in an infinite loop in our code, but we'll see. Alright, these rules specify the required contents for 9 bag types. In this example, every faded blue bag is empty, every vibrant plum bag contains 11 bags, and so on. You have a shiny gold bag. If you wanted to carry it in at least one other bag, how many different bag colors would be valid for the outermost bag? In other words, how many colors can eventually contain at least one shiny gold bag? Okay, so we have a containment problem where a bag contains other bags. And now what we want to know is, for shiny gold bags, which other bags can contain it? and not only which ones can contain it, but which ones can contain them recursively going back up the tree. So that's a graph traversal problem, and our graph traversal problem is, well, depending on the depth of this tree, it could be, or it might be tractable as a recursive problem. Sorry about that. Yes, thank you. Welcome. Yeah, I'm not yet used to streaming well enough to realize that I don't always get my screens right. I'm sorry about that. Thank you for reminding me. Yeah, so the problem we're dealing with, I'm just going to recap real quick. They've given us a set of bags, each of which can contain 0 or more other bags, and when they contain other bags, it's describing a directed graph. We believe it's a directed acyclic graph, because it wouldn't make sense for a bag to contain itself, or a bag to contain, duplicates of itself. Although I suppose if you're using duffel bags, you could maybe come up with something that would work, but let's pretend that's not true, at least until we're shown otherwise. So we've been given a description of these bags, and then we're asking, if you have a shiny gold bag, how many different other colors of bags could you have that could contain that shiny gold bag? So, and that's going to be we're going to start, I think, with a recursive algorithm down the list of contained elements. And we'll see where that goes. But basically, we have to count the number of unique objects that have a tree that contains a shiny gold bag. It was a Bagdag, yes. Excellent. I hadn't put it in so many words. That's the best. A Bagdag. I love it. Okay, so let's take a look. It says the list of rules is quite long. Make sure you get all of it. So, oh shoot, I didn't set up beforehand with my editor for the day. So let me close this and set up the editor. So, day 7, enter. And now I can cd day 07 vc dot and then park this guy side of my screen. All right, so our sample input file, which we are definitely going to play with first because this could possibly get big and slow and ugly, is going to be that, and we are going to have to parse this. And then the puzzle input is a whole lot of these, so copy um 594 lines of colors. Now, just looking here, so there's a couple of things that we need to know. One is that color descriptions seem to always be adjective color, just 2 words, and that's good. We may store them in our data structure separately because part 2 might ask us to do something with grouping colors or something like that, and I don't want to mess with that. I mean, maybe it's just randomly generated and I don't care, but let's let's be, I think, better safe than sorry. Another thing that we need to notice is that just from the although the example, everybody had exactly 2 colors, in this file, in fact, is two types of bags that it could contain. This even line 1, striped tan bags contain 2 light silver bags, 1 drop bag, 2 clear, 2 mirrored, etc. Clear tan, interesting color. We have to have basically an arbitrary number of children in our tree, or in our data structure. It's not necessarily a tree yet. And syntactically, these are worded, in a way that is going to be reasonably easy to parse. They have, if it's 1 bag, it doesn't say 1 bags, it says 1 bag. So we have to cope with the fact that the S on bags is optional. Or, not optional. It indicates that it's a 1, but I don't think we really care. If it said 1 vibrant indigo bags, I think we should still parse it. Separated by commas. So this is one of those things where it's simple enough that we can just basically parse this by words and assign them split this up. I don't think I want to use a regular expression for everything here, because groups of regular expressions are A, hard to understand, and B, kind of hard to deal with in the structure in the API. So instead, what we're going to do is read each line and pull out things that look like adjective, color, bag, S option. Separate them by commas, and we'll be able to build our data structure. So, all right. That gives us an input sample. So we're going to write a parse function this time rather than just doing it in split. So let's, right now our input function has, reads input and splits it into lines, which is exactly what we want here. And then we're going to parse each line individually. So we're going to define a function parse line, which takes, let's do parse lines, which takes an array of lines. Lines, array of string, and that will do a for underscore comma line colon equals range lines I think we'll do it in a separate function in case, I don't know, just feels cleaner that way. Let's write the parse line function first. Okay, so I guess I'll make that an optional too. And then double that. Okay, so and then there's a period at the end of that whole mess, but I don't think we care very much. All right, so what I'm going to do is I'm going to split I'm just trying to think about the best way to split this up. If I just split on space, actually, if I split on noise letters, no, split on space, comma space, comma or space, comma and or space, then I can get okay. This was this may be excessively clever, but if I do a pattern that looks like this is a regular expression, and the regular expression is going to be either a space or a comma. Maybe I want to do this in space or comma space or even better, bags space bags period or bags comma or bag period or bag comma or bags contain so then what I'm going to end up with when I do this, how did they say no contains no other bags? That's an alternative for the oh no, actually here we'll do this. Or just bags contain. Does this work? So what I'm trying to do here is I'm going to split on this pattern. And if I split on this pattern, then what I hope to get back out of it is essentially an array. Once I do a find all matches, what I'm going to get is the first match will be what's left of bags contain, and the rest of them, any more that there are, will be number, adjective, color, is what I'm hoping to do. And actually, I should put a leading space in all these so I don't have to deal with the space and the color. And my concern here is that I may have, I don't know for sure if the pattern, I want the pattern matcher to be greedy. So I want bags contain no other bags to be matched for sure. So I want the longer pattern to be matched. And I think that is the default behavior, but I'm going to check to be sure. Regexp. What? That's in Python. I want Go. Okay, you put the question mark if you prefer fewer. We want to prefer more. So that's good, that's the default, and that's what we're going to do. So we're going to do, okay, so now we have this. Pat is actually, this is regex dot must compile. And now that we have that pattern, we are going to matches is pat dot find all string, and there are no submatches because I have no parenthesized expressions. So find all string in line, and we're going to put -1 because we want find all matches. And parse line is going to return our data objects, and we need to build the data objects first. So let's call these bag is a struct containing bag is a struct that contains quantity, which is an int. Now we don't actually need it for this thing, but I bet we're going to need it in part 2, so I'm going to put it in here. Adjective is a string, color is a string, and children is a slice of bag, which could possibly be empty or null. We have to decide semantically which one we want. And no, we want this to be an array of pointer to bag. I'm just thinking another way to do this would be to store these in a big array and have the children be references within the array. I mean, it's a fairly classic way to store this thing, and a way you would do it in a lot of languages. It would likely be faster because the elements in the array would be contiguous and are therefore cacheable and other things. I don't know how deep this is going to go, but there are 600 of them, so deep-ish anyway. Let's maybe do that. So parseLine is going to take I'm arguing with myself about how badly I feel about having a global array here of bags. Best practices would mean I would probably want to pass that thing in and update it and have these functions manipulate that. But in the interest of doing it quickly, I think I will just have var bags is an array of bag. Let's actually assign it. And we're going to put no elements in it. Although actually when we call parseLines we could... Oh, that's better. Let's do it that way. Quantity should be associated with the child, not with the parent. You're absolutely correct. That is totally true. Wow. That's fascinating. Yes, good, very good point. Thank you. So Coriolanus said, quantity should be associated with the child, not the parent. It's possible to have shiny red bags contain 2 striped green bags, but also faded chartreuse bags contain 3 striped green bags. So that is absolutely correct. And I was going to figure that out sooner or later. But it was a good catch. So quantity wants to not be in the bag structure. It wants to be associated with the bag. So there's a bag, which has an adjective and a color, and the types of bags that it can contain. And then it's not just the types of bags it contains, but the quantity of each of those types of bags that it contains. So it's not an array of int, it's an array of another type. I'm going to call a type containment, which may be int quantity and sorry, which language am I writing in? Quantity int and child indices is an int. And in this case, instead of calling this child indices now, let's go back to children. Is an array of containment. Slice of containment. Now, even though these are internal types, in this kind of case, I often just make them capital, public, I don't know, and then Go yells at you, the editor yells at you to put in comments. Containment indicates how many children of which index is. Why is this still? Oh, just editor glitch. So, if I were to make the number of possible bags an array, then I need to initialize each of those appropriately. If I do it with make, I think I'm going to append it and construct them as I go. Not type. Func new bag of adjective string color string quantity and what that's going to do is construct one with an empty array for containment. Oh, and then quantity. No. Sorry. That creates a new bag. And then we can have an add child. So here we go. So we'll do this. There's a bag. And so return bag of adjective j, comma, color, colon, call, children, colon, make, or a slice of containment that is of 0 length. Okay. And then that's new bag. And then type. Whoops. Shit. Sorry. It's supposed to be clean. I am parsing this, and my problem is I need to make those links to things that may not exist yet. So if instead of an array of these, if I had a map of them indexed by name of color, I'm concerned about that from a performance point of view, but maybe it's not that big a deal. So the good news is this is actually a more interesting just the parsing of this is kind of fun. So, jeez, what am I going to do? I am going to, instead of this being an int, I'm going to change this to a string. And children is still an array of containment, so that's good. That's fine, we can do that. But now containment is going to be string, which is the name of the child, color. Sorry, I'm thinking aloud. I'm thinking not aloud, I'm thinking quietly. What I'm curious about is I've been map keys. What I'm curious, what I'm trying to remember is that doesn't work. All right, we're gonna search in here. So in C#, which is what I've been working in a lot lately, you can override some functions and provide your own keys for data structures so that you can store them in a map and control what is the key element of the map. So what I was wondering is, can I define something that says adjective plus color is the key? And user-defined key with user-defined equality. Strict comparable semantics for your values. You cannot define your own cache code and equality functions for map keys as you can in many other languages. Okay, so we're doing that. I'm just going to store them as strings. It's not worth it. Yes. Coriolanus said, as far as I know, Go still doesn't allow custom types as map keys, unfortunately, which is true. So, yep, I've been away from it for a little while. You know, we could define these with a essentially get key function. And the get key would concatenate adjective and color, and then we would use get key everywhere we want to do keys. And of course, as that Stack Overflow item we were just pointing at noted, if that's not immutable, if that might change when somebody modifies the data, you can get yourself into real trouble, because now the thing that was in your map is indexed by a value you no longer have access to, or something horrible like that. So don't mess with that if you don't know what you're doing. In this case, although we could do that, I think it's probably just easier to store these as strings. I think I'm just going to leave, not even create a new containment object. And so now we have our matches, and now we have bags, and children are containments, and containments are other children. And instead of storing them in, I had been playing with the idea of storing them in an array, but we are now going to do a map of string to bag, and then we don't need to size it anymore. So we've just parsed our line of matches. Why did... Oh, okay. And now if... No, actually, if matches is null, we'll just do that for now. If it ever breaks, we can add some more debugging. But basically, it shouldn't ever fail. But in case it does, we'd like to know that we got the pattern wrong or something. Let's do fatal F line percent %s on the line. There. Now if it fails, we'll know why. We can figure out why it failed. But it didn't fail here, and so now we know matches of 0 is going to be the thing we want to create a bag for. So we're going to say bag is new bag of, oh, whoops. Our matches are themselves strings. So we just got an array of strings. So we have to parse each of those as well to make bags out of them. So let's parse bag of s is a string, and we're going to return n as an int, yeah, I'm going to return a bag, duh. We're going to return a bag, but it's going to be a bag with no containment in this context. And we're also going to return a quantity. All right. So in this case, our pattern is a excuse me. We get syntax, and our character class that we want is so what we have is either something that looks like dull plum or that looks like something like for wavy indigo. So our pattern is an optional I'm going to mark it, I'm going to wrap it in parentheses, optional color digit. So an optional digit, a space, not just a single digit though, it's possibly n, where n is more than one. So I'm just going to go star inside the parentheses. And so worst case is that sub element will be an empty string. And then I have another sub element which is colon lower, which has to be at least one letter, so we can put a plus after it, and then another space and another one of those. And now in this case we're going to do matches, oops, exp dot must compile, and then matches are going to be pat dot find all string submatch of s minus 1, and then it's going to return an arrays of strings, or a slice of strings. And so now for underscore match is in the slice of matches, and for, well, no. What we're going to do is we're going to say bag is a new bag that gets match of, so match of 0 is our whole match, match of 1 is the digit, match of 2 is lower, is the first argument, match of 3 is the second argument. So we're going to go 2, match of 3. So now we have a new bag which has an empty array of children, and we are going to return that. There's no range of matches. What the hell am I thinking? Fine, not all string submatches. Just find string submatch. This is my, I'm sorry. I'm confusing everybody. So this should have been a find string submatch because I'm not at the top level, I'm at the next level down. And then, so it's no longer a find all, so we can just find the string submatches, and then there are still, I'm right with this, but I don't have a loop. There's no loop here. And then return n So if that came back blank, then this strcconf is going to error, but I don't care because in that case n will come back as 0, which is what I want. So I'm going to just return now return n bag and match. It's no longer matches, it's match. So actually I should fix this. There. All right. So we're going to call bag here gets to be a new bag, or gets the result of parse underscore comma bag, because I don't care if it's 0, parse bag of matches of 0. So I'm going to take the 0th element, which is the first thing in the line, and say make a bag for that out of me. And now I'm going to iterate over the remainder of the line. So for be in range matches 1 colon. So in other words, that's the remainder of the line. Bag of children equals parse bag of B. And I think I'm going to change this to oh crap. Yeah. Oh, and also that's just wrong. So let's do this. N child is parse bag of M. Equals child dot adjective no, let's do this just to be safe. Func bag name string returns the string, which is, so we're going to return b.adjective, and just to preserve readability, we're going to put a space in the middle of it. And also that will avoid us any problems of concatenating like short words like tan and maybe having it be something else also valid. So by having the space in there, it's just safer. So I'm going to give this a comment, or it's going to yell at us. Name turns up canonical name for the there. Now that's a safe way to construct containment. But the problem is I also need to, well, no, that's all right. So I have a bunch of names. This needs a comma. And it's also, I need an append of bag of children. No. Wait, what happened here? I just went to the wrong line. That's better. Alright, so bag of children now grows by 1, so we're going to have a bunch of children on the bag. And then we are finally going to store the resulting bag in a map. So this is where, or no, we're going to return the bag that we've just built. And of course, stop it. Why is it saying it's not? Oh, bag dot children. Wow, I don't know what I was thinking. Bag dot children. Bag dot children. That's better. Okay, so this parses a line, it returns a bag which has all this stuff in it. Bags now is made from string bag, so so now I can say bag gets the result of parse line of line, and it's no, oh yeah, and now I say bags of bag.name equal bag. Cool. Now there we go. All right, now we're doing pretty well. Here we go. So now we should have, when we run this, an array, a map of bags when we call parse lines. In order to make sure that it's doing okay, we probably want to, let's see what we get. As long as we're doing this with sample data, it's not going to be terrible. So, wait, there's at least one error here. Except I don't see it. Oh, there it is. Wait, parse lines. Oh, needs to return bag. Alright, no errors left. Now... boom! Okay, index out of range with length 0. And that occurred on main.go line 43, which is here, where we constructed... we tried to parse the bag with this pattern, and it didn't work. Oh, that's because there's no leading space in that. I'm going to make this space optional. Try it again. Yeah, still didn't like it. So, alright, I have a string of digits, 0 or more of them, with an optional space, followed by a lowercase word in space, followed by a lowercase word. So, let's do this. Since it's probably failing very early. Let's just print the string that we're getting and see what happens. Bags. Oh, I didn't want find all string. I wanted the opposite. I wanted to split it. Dummy. Oh, did want the -1 in there. Alright, how many... Okay, let's try it again. Light red contains one... contain one bright red. Yeah. Oh! Guess what? That has to be backslash dot. The dot in these is meaningful. Commas are not, but periods are. Dot means any character. So let's try this again. Okay, it's yelling at me in red. That's why that's red, because it's wrong. Oh, I guess I need, because this is not a raw string. Maybe I can use single quoted string rather than escaping the backslashes. It's probably a better bet. No errors now. Light red, 1 bright red, 2 muted yellow. Oh, I had a leading space for 2 muted yellow. That's because bag comma needs a trailing space. So parse bag, S is sometimes coming out as blank. Sorry if this is boring. All right. Why is this blank? Parse lines is parsing a line. Parse line is taking this. It's doing a split. Oh, and the last element might be blank. So we don't want to call parse bag. Let's just do this. Hey, there we go. Okay, we passed all of that. We got one more here. Faded blue, dotted black. So what happened here? Our sample contained no other bags. Oh, and I have a blank line at the end, which is confusing as well. Just save that. Sweet. All right. Now I can get rid of my format.println here. And we get a map, bright white, which contains, bright white contains one shiny gold. Now, is this true? Let's make sure this is true. Bright white bags contain one shiny gold bag. Dark olive contains 3 faded blue and 4 dotted black. Dark olive contains 3 faded blue, 4 dotted black. Okay, looks like we got this. Great. Now we can move on to actually evaluating the result. All right, so now we have a map. That map contains bag entries, each of which might have some list of children. We identify the children by their name, and we store the whole thing in a map of name to bags. So now the question is, we need to start with shiny gold, and we need to traverse this list looking for all the bags that contain shiny gold as somewhere in their tree. And we need to count that number that we find. So what we can do, the simplest but slow way of doing this is that we just iterate through the map, and for every map we just call it recursively down all its list of children, and if we ever see shiny gold we can just return true and come all the way back up the tree. And that's certainly going to be fast enough for the input sample. It may not be fast enough for input. So I'm going to try it, see if it works, and if it works we're going to go from there. If it doesn't work, the way to do that is you could do you can take the bag object and you can decorate it with basically a flag that says, does this contain anything? So that once you've hit something recursive, you can, oh, actually, yeah, we can do it this way. Yeah, let's do it this way. I'll walk us through it. All right, so I'm not going to print my bags anymore. And so let's create a new function for this, for our part func. Day 07a takes a map of string to bag bags and returns an int, since that's what our result's supposed to be. It's the count. Oh, and just to make it a little easier, target bag is a string. So one question I have now is, shiny gold is excluded, so the bag itself is excluded from search. So there aren't 5 ways to hold a shiny gold bag, there are 4, because shiny gold itself doesn't count as part of the list. So we're going to make a separate map of string to, so we're going to say, here's our list of founds. So we're going to found is, this is, we're back to sets again, but this is found as a map of string to empty struct. And we want it to be empty. Now, for so we're going to find the name in the bag. So we're going to iterate through the list of bags. If name is the same as target if name is target, then continue, because we don't care. Otherwise, so we're going to look at a bag. Now we want to look at that and if it was the target, we're going to skip it. If it's not the target, then we're going to look at its children and see if the target appears in any of those children. We're also going to test if any of those children are in our list of founds, because if they are, we're done. In other words, if we say, well, if we say a blue bag contains a gold bag, and then we look at a green bag and a green bag contains a blue bag, then we know that a green bag could contain a gold bag, and we're done. So we can shortcut the search. So, for child in the range of bag.children, okay, I have a recursive routine I need to write, and this caller day 7 probably shouldn't be the recursive routine. So let's do this. So for search part A, we're going to accept and search is going to record an integer, but search is also going to take the found array. So we're going to do the found array and make it part of day 7, and map of string struct. And why is this upset? Oh, no, that's correct. Search A. Oh, curly brace. There we go. That makes much more sense. Okay, good. There we go. Sorry about that. So, children's array of containment. And what I want to say is if child dot child is target, turn, oh yeah, this isn't returning an int, this is returning a bool. Return true. If child if found child underscore comma okay colon equals, so if we try to look it up in the found array and we found it, then return true. Now that I've done this, I'm not happy with the name child here. I'm going to change this to name. So rename the symbol to name. And then that's going to read a little better. Get there 1 second. Okay, so for a child in the bag of children, if it's named, if it's found, return true. Otherwise, search. What am I searching for? have to... Do I not have to do this recursively? I was thinking I had to do this recursively. No, I do. But then... No, I'm searching iteratively. Hold on. Phew, I'm having a little tough time today. Sorry about that. So I have a list of... I have a map of bags, and I'm walking down the map of bags, and I'm saying, okay, does a blue bag have anything in it? If it doesn't contain gold directly, it might contain gold as a child. The problem is... Oh, yeah, that's right. So, for each of the children, I am asking if the map contains yeah, no, this is correct. Otherwise, after the for loop, if I haven't returned true, I return false. That was a little tougher than I thought it needed to be. Okay, so now if we found the target, so search recursively searches all the children and all the children of the children, etc., until it either returns true or it doesn't. If it does, then what we need to do is add that item to the found list. So found of that was kind of silly. I need to iterate the range of bags at this level and then recursively search for each bag name that I have. Whew. All right. So if the name is the target, we just continue. If found of name is struct, so we add that item to the struct. And can't I think recursively today? I don't return false, I return Alright, did I do this right? Feeling a little stupid right now. So, alright, I have a search. And I am... So, I make an empty map of found elements. Then I iterate over the range of bags. And I say, well, if it's the target, if it's the gold that we're looking for, then just continue. Otherwise, I call this recursive search function with the name, the bag I'm currently using, and target, the full set of bags and the set of found elements. So then this is a recursive routine which takes all those things and it walks through all the children. So our termination conditions are, if the child is the target, then we found what we're looking for. It's definitely true. This item we're searching for is in fact true. It's a valid container of the gold bag. If it is already in the list of found names that we've already processed, then it's also a valid container. We don't have to search any further. We don't have to recurse anymore, so we're done. Otherwise, we're going to do a depth first search, and we're going to look at the list of all of the children and search them remotely. So we're going to take and basically say, okay, so we found the child's name. Now search based on the child's name and do the same search and if that returns true, then it's also the case that this can contain the bag. Otherwise, after going through all of that, we return false. If the result was true, then we add it to the found list and we call for the next one. So we're basically walking through the list and periodically adding items to the found list. And when we're done, we're going to have in the found list the list of all of the names of all of the bags that could contain a gold bag. And so we can just say, how big is that list? And return that number. So now that we have parsed our bags, we're going to do a Day 7. Oh, target. And I'm going to rename search bag to target since that's the name I'm already using for other things. Rename that symbol to target. That's a little happier. This should now compile. Yeah. Yeah, I was kind of realizing that as as you were saying it. Okay, so Coriolanus says you could write day 7 recursively. He tried to paste in some Python pseudocode, but Twitch stepped on it. Yes, once I teased it apart, I realized, yeah, it would work to have it be one function that calls itself recursively. It would need a couple extra parameters, but it's fine. Once I got to the point of saying, oh, this could be consolidated, I didn't bother to refactor it. Let's try it like this first and then see where we are. So we're still using sample data, and 4 bags were found that could contain shiny gold. That is the right answer. So now I'm semi-optimistic that we got this right, and I'm going to change it to input.txt and see whether I'm actually correct. Let's see. Also want to see how long this is going to take to run. Oh, that was pretty fast. 302. Do we believe that? There were 500 and some odd. I think that's a reasonable number. It's certainly not too big. And, without, deeply analyzing the data, which is exactly what this is for, I don't know really how that's going to be. But I'm going to try putting 302 in here and make sure that, and see whether we're correct or not. That is the right answer. Okay, yay. Part 2. Now let's see what's going on. You have to buy so many bags. Consider again your shiny gold bag and the rules. Faded blue bags contain 0 other. Dyed black bags. Vibrant plum bags contain 11 other bags. Dark olive bags contain 7 other bags. So a single shiny gold bag must contain 1 dark olive bag and 7 bags within it, plus 2 vibrant plum bags, total for 32 bags. Of course, the actual rules have a small chance of going several levels deeper, even if the nesting becomes topologically impractical. Okay, that makes me worried. Now, if this had... I think topologically impractical is just... I mean, I don't think we could have a situation where this was a cyclic graph, because if it were a cyclic graph, then we would have gotten stuck in a recursive routine. Because it would just... Oh, no, maybe not. Well, our found loop... Because our found loop... for loop may have broken any possibility of cyclic, but let's try and see what happens. They gave us a second input sample. And yeah, we can probably test with that to make sure that we're okay. So this is where the quantity of bags at each level. It's also a different thing. We're basically saying, okay, how many bags do those contain? How many bags do those contain? Etc. Etc. It's actually, I think, an easier loop to write. And so I am going to write a function. Well, let's first write the call to it. All right, so now we're going to write day 7b. And I'll put it there. Let's do day 7b down here. So day 7b has to recurse in the opposite direction. Basically, we're going to start with go bags, and then we're going to say how many children does it have, how many children each of those have. And so our simple recursive routine is actually just, we can use D7b directly, recursively, and keep track of the number of children each of them has until they get to 0. So that's just going to be for a child in the range of Baghdad children. Oh, so this day 7b is all right. It's not a necessary variable really, but I'm doing it anyway. So child is bag of children. For each child, we need a total. Times child.quantity. So if you have 2 I'm going to try it with the plain old input sample. And then here we're going to return total. So day 7b is probably actually better renamed, even though it breaks my pattern count. in children. Cool. And this is, yeah. What did I do wrong? Oh, because this is %s. Zero on the bags. Okay, I did that wrong. Total 0 for each child in that bag's children. I'm counting the bags. So let's just take a look. Input sample. Light red bags contain 1 bright white. There's no zeros there. Oh, times. Ah, wait, hold on a second. Count bags and children. So a gold contains gold, 1 dark olive. And that's going to be 1 times dark olive bags contain 3. Faded blue contain 0. So that's going to return 0. So we don't want to return 0. That's not the right number. 32 is the right number. Oh, wait a minute. That's not right. Okay, hold on. I'm not thinking about this clearly. Bags and children. Oh, so it's not this. That's not the right number. Total count bags and children is, it's that number. So if I have a blue bag, the blue bag counts for 1. If I have 5 blue bags, the blue bag counts for 5. Even though each of them has no children. So it's it's 1 plus this value. That's the right value. Okay. That was not great. But okay, got it. So now we are going to, we're going to test on this one just to be sure that we're still getting the right answer. So we're going to make an input sample 2.text. And paste the contents in here. Save that. Go to main.go. put input sample 2 and run this. 126, which is the right answer as well. So now we feel pretty good about this, and we can go back to the main input.txt and run that. 4,165 bags. That is the right answer. Hallelujah. That was a little longer than it probably needed to be. This is one of those cases where had I done it in Python, I probably could have pulled it off a lot quicker. But yeah, it was fun to noodle on, even if I wasn't necessarily thinking as clearly as perhaps I could have on other days. But we solved it. Yay. And so that's that. So just to wrap up, we just solved Advent of Code Day 7. It was a recursive walk of a directed acyclic graph. Once essentially accumulating results on the way back up the tree, and the other one looking at, accumulation from below the target point. We dealt with those with recursive subroutines. We were pretty confident that our data had no cycles in it, that it was an acyclic graph. That simplifies a lot of things when you do that. The technique we used to maintain the list of visited items might have saved us from a cyclic graph, although I didn't really take the time to analyze that. But let's you can do that in a cyclic graph. You can keep track of visited nodes or something like that. Sometimes you see, decorate the nodes or mark the nodes in some way. In our case, we were doing it by keeping a separate list that wasn't modifying the node's data structure itself, which is usually the safer way to go, particularly if you're looking at like a data structure that might be traversed by multiple threads. You don't really want to scribble on the data in a way that you're going to have to undo later. So that's that. We have done it. I'm going to actually, in case you want to watch, I'm just going to commit this, commit the whole mess. Let's see, delete main.py, because we just aren't going to do that today. And I'm going to, oops. Stage 2, so solve day 7, both parts, and then git push origin main. There we go. So that's up on my website. I'm sorry, up on GitHub. Just to remind you, my name is Kent Quirk. I am Kent Quirk on pretty much all the media, including on GitHub. If you want to see these sources, feel free to spelunk them on GitHub. And I hope everybody has a good day, and I'll try and see you again tomorrow. Good night.